Our speakers this evening come from PingCAP. Please welcome our second speaker of the evening, and Huang, Co-Founder and CTO. But our first speaker of the evening is Kevin Huang.
Wow, that was quite the opening act. I was not expecting. I'll be talking a little bit louder. Since I don't have a mic, it's my bad, not Eric's bad. Thank you again for having us. Thank you, New York City, for having us. I'm actually based in the San Francisco Bay Area. Ez has never been to New York City until this trip.
It's my first time doing, yeah, thank you.
So he's loving it right here. So today, we're going to tell you about TiDB, which is an open source distributed relational database, how it works, who's using it, also the background behind this product, in case you guys are interested. So let's go through that. Here's a quick agenda of our talk today. I'm going to give a quick company history and community overview, as well as an architecture overview. Ed here will do a really deep dive into how this database is MySQL compatible. Why is it so? How do we make that so? And the rationale behind all that. And then I will go through a quick use case study of one of our biggest customers called Mobike, which is one of the largest dockless bike sharing platform in the world, actually. I see a lot of dock bike in the city, like the city bikes and stuff. So it's that minus the docking. So you can leave it wherever you want. And then last but not least, Ed will do a couple of demos, one on how you can run TiDB in the cloud anywhere using Kubernetes, which is this up-and-coming ecosystem of cloud-native tools. Of course, we'll do another demo on TiDB Syncer, which is a MySQL-compatible tool. We'll get into all that and what that means. And then Q&A, and of course, a Google Home Mini raffle. Okay? So again, a quick introduction about ourselves. I'll just do an intro for you, Ed. So he's the co-founder and CTO of PingCAP. He's done a lot of work in the infrastructure engineer space prior to founding this company and starting to build TiDB in places like Microsoft, Netease, Wandou Labs, and of course PingCAP as well. That's his email. You can email him whatever you want. And a little bit about myself. Again, my name is Kevin Xu. I'm the general manager of PingCAP's US, but really now North America office here in North America. I study computer science and law at Stanford. If you think that sounds confusing, trust me, it was even more confusing when I did it. And that's my email. If you want to bother me, if you want to work at PingCAP after this presentation, email me. That's all good. We're hiring for sure. A little bit about PingCAP, the company. It was founded about 3.5 years ago by 3 infrastructure engineers, Ed being one of the 3, of course. And the core product that we make is this thing called TiDB. Ti just stands for titanium. There are 4 main components to this. One is TiDB, the SQL layer that is stateless and MySQL compatible. That will be kind of the main topic of today's talk, since this is, to my knowledge, a SQL crowd. We also have a distributed transactional key-value store called TiKV. We have another component called TiSpark, which leverages the Spark library to be able to do complex analytics in the same system. And then this thing called placement driver, which is this metadata layer that does a lot of the scheduling, the replica, the metadata storage, and also timestamp service to be able to keep transactions, because we support a strongly consistent relational transactional database. And it was open source from day one. It was inspired by the design of Google Spanner, which is like a Google project that I think is now part of the cloud offering as well. Also, F1 is another Google project that inspired us to design this thing. And then our GA was in 2008, earlier this year, our 2.0. And these are the core features of TiDB. I won't list them because we can all read slides, but we will actually talk about how we can make all these features so, as opposed to just tell them that we can do this, so you understand the technical background behind how this was made possible. And because we are open source product, it's good to share some community stats as well. So TiDB is actually one of the most popular and highly starred database projects on GitHub. It has a combined, close to 20,000 stars. We have 200 or so contributors. And just to give you some context, our company only has about 100 people. About 75% of those folks are engineers working on this. So of course, the vast majority of the people who are also working on this product are not from PingCAP, but folks from other companies or community members or just hackers who like to build databases. a few recent news to share with you guys. We announced our Series C funding a few weeks ago, a $50 million round. We also open sourced this thing called TiDB Operator, which is a Kubernetes-based operator engine that helps you deploy this database in any cloud environment. And another news that we announced recently is that TiKV, which is the KeyValue storage layer, is actually now part of the Cloud Native Computing Foundation. And for those of you who have never heard of CNCF before, so they're kind of an offshoot or a subsidiary of the Linux Foundation that particularly drives cloud native products and projects. So Kubernetes is part of that. Prometheus and other kinds of things that you might have heard of in that world is a part of that foundation as well. And now so is TiKV. And last but not least, yesterday, InfoWorld recognized TiDB as one of their top open source database projects for 2018. So that was pretty cool for us to discover that the day before we're going to give this talk. All right, so now I will go through a quick architecture overview before we do the MySQL deep dive. I know you guys probably will have questions throughout the the talk. Feel free to raise your hand, but chances are we will probably answer your question in later slides, as often how these talks kind of unfold. So let us know how that goes. So again, I want to remind you guys of the three major use cases actually before we talk about the technology, so you have an understanding of why people use this database or what is the point of it to begin with. The first thing is MySQL scalability. So the big problem we're trying to solve with this database, and that's how a lot of users are using it, is if you are using MySQL now and you have trouble scaling your operation and your database, don't do manual sharding, don't break up your tables and do all that kind of traditional stuff. TiDB offers scalability right out of the box. All right. And the second architecture use case is that a lot of companies now are trying to combine traditional, transactional, and analytical workloads all in the same system. So you don't have to have this delayed ETL process to port data from one database to another, say like RDS to Redshift or that kind of a workload. You can do all that in TiDB, the entire system. So you can actually achieve pretty much real-time analytics on live transactional data. And the third big use case is a lot of people are using TiDB as this unified storage layer. A lot of our users, when they design the architecture, has a mixture of Mongo and Redis and Cassandra all in their architecture, and they had a lot of pain point managing all those things at the same time. And a lot of them now are using TiDB and TiKV as the single source of database systems. So they only have to manage one system and can support all kinds of application services. Okay? So I want to keep you guys kind of think about these use cases as you learn about the technology today. And this is how we make it work. So this is kind of the broad overview of the architecture. The three components that I mentioned, TiDB, TiKV, TiSpark, placement driver, or PD, are all separate components. And TiKV is the distributed key value store where the data is actually persisted. So that's kind of your storage capacity. And then TiDB over there is the MySQL compatible layer that is stateless. And so is TiSpark, which is the Spark plugin. So you can actually imagine these two kinds of resources, right? One is compute, one is storage. All can be scaled independently of each other, whether it's in or out. And that is essentially what a cloud native architecture should do, is allow scalability in whatever resource that you need. And that's how we designed this database to be able to do that. And because TiDB and Spark talks the same data source, TiKV, you can do analytical and transactional processing all out of the same system, right? And that's how we make this hybrid architecture work. And a quick overview of how TiDB works with TiKV. So TiDB, the SQL layer, again, is actually something we made from scratch. And Ed will talk more detail about why we did that. But that is the MySQL-compatible layer that has our own SQL parser, our own Costbased optimizer, and also a co-processor layer, which is how we can do push down into parallel processing. So different TiKV machines can process the same query simultaneously to improve performance. And TiKV is where all the data gets essentially automatically sharded into smaller chunks. That's what these squares are. And they're replicated to achieve high availability using the Raft consensus protocol, which is this consensus protocol that's been around for a few years now. Paxos, you guys might have heard that as a much older consensus protocol, but those are kind of a couple options that are out there to do consensus. And RAP is what is known as a leader-based consensus. So literally you have three copies of every single chunk, and they vote. And if you have majority kind of quorum is what they call it, then the data is kind of consistent, and then you can serve up that data after the commit is made. And we can dive into deeper into how RAP works if you guys are interested. But that's kind of how TiDB works with TiDB. And kind of like my point, we're in 2018 now. Please don't any more static sharding, because that's really just stat-based for the DevOps and the database administrators and architects that are out there. It's very, very difficult to manage. We didn't really have a good solution for this before until databases like TiDB came along to build this automatic sharding and replication and consensus for you. So you can just keep on throwing data into the system and not have to worry about consistency or your capacity. And this is a quick dive into TiKV, which is really the foundation of the entire platform. Again, I mentioned things like coprocessor API. It has a raw transactional KV API. RAP is in the works. And under each TiKV instance, which you can imagine as physical machines, there is also an instance of RocksDB, which is this really powerful storage engine that Facebook open sourced a few years ago that supports a lot of open source database. Here's a quick overview of TiSpark, which is essentially we kind of brought over the Spark execution plan, and then have it be able to work with both the placement driver as part of the platform to be able to retrieve data location, and also work with TiKV where the data is actually persisted. And this has nothing to do with TiDB, as you can see. So you can scale TiSpark and TiDB independently of each other, depending on what kind of workload you need for your system, for your business. And the last but not least, the piece we most recently open sourced is this thing called TeddyB Operator, which is a pattern inspired by the folks at CoreOS originally that leverages Kubernetes to be able to essentially simplify and automate a lot of the stuff that you used to have to do by hand, like deployment, managing, scaling, upgrading, maintenance, this large cluster of distributed system. We can all build that into this operator tool, and that's also open source, so you can check that out in that link. And we'll send all this deck to you later on, so you don't have to write the thing down. Okay? With that, I'm going to hand over to Ed to do our deep MySQL dive on how TeddyB works specifically.
Yeah. Hi. Hello, everyone. It's very glad to be here to talk about TiDB's SQL layer. The first question is why we choose MySQL protocol. I think as the founder of TiDB, in my opinion, we should choose a big community. We should choose a well-known community to embrace with. And MySQL has a big community, but just like Kevin mentioned, scaling MySQL is a little bit tricky. The DBAs. I used to be a DBA. Keeps working it around, and the application developers keep sharding, but after the sharding solution, like the table sharding, you cannot do something like cross-shard transaction. You cannot do something like complex join, group by, things like that. And you have to specify the sharding key everywhere in your code. So and on the other hand, maintaining a large sharding MySQL cluster it is not an easy job. So you cannot do things like, for example, if you want to do something like DDL or backup restore in the large sharding cluster, it is very painful. So that's the problem TiDB wants to solve. And our target is, if you are using a standalone MySQL right now, you don't have to change single line of code to migrate to the TiDB solution, and then you have a scale out solution. And I just want to say, my TiDB is not the dropping replacement or the replacement to MySQL. we just complements MySQL. For example, if your data is not that big, if your MySQL still working well, MySQL is still your best choice. TiDB is designed for large scale data, and for us, using MySQL protocol brings another benefit. So we can just reuse the tests from MySQL Codebase and other software that relies on MySQL. So there's a saying, writing the database is not hard. It's not that hard, but the real hard part is how to test it, how to prove your database is correct. In our case, we have more tested code than the database core, and because we speak MySQL protocol and compatible with the syntax and MySQL the grammar, so we can use MySQL integration tests from the very beginning. And what's more, we even create a tool, for example, to record the request and response between the application, like WordPress or something else, to the application with MySQL, and we record that workload and to TiDB and make sure our behavior is keep the same with MySQL. So that's how we test it. And if you want to build a MySQL compatible database, the easiest way is just reuse MySQL. At the very beginning, about 4 years ago, the architecture is like this. We just replaced the InnoDB part of MySQL, and I even wrote a prototype based on RocksDB storage engine. Back in the time, the project became the MyRocks, but back in the time, the name is RocksDB storage engine, and the architecture is very similar to the Amazon Aurora, right? But I think everything has its pros and cons. This architecture, the pros are first 100% MySQL compatibility, right? Because we just reuse the MySQL front end, so everything keeps the same, and it is quick and dirty. I remember I only used about 3 or 2 weeks to build a roundable prototype using this architecture. But the cons are also obvious. First, the SQL layer, aka MySQL, the SQL layer isn't aware of data locality, so that it's really hard for the SQL layer to push down the computing logic down to the storage node, because the SQL layer doesn't know the underlying storage is a distributed system. And another thing is, if you want to do some cross transparent ACID transaction between multiple nodes, MySQL front end doesn't know how to talk to each other. So handling the logs across different MySQL instances will be very tricky. It's very hard to implement. And MySQL is a 20 years old project. It is written in C. Well, as a founder of startup company, I just don't want to maintain such a huge C project. So we decide to build our own SQL implementation. The first thing is to choose a programming language. We choose Go. Go is very productive, and as you can see, many recent projects are written in Go, like Kubernetes, Docker, things like that, written in Go, very popular. And also, it is my favorite language. I used Go for a very long time. I remember before 1.0, I started using Go, building for building many systems. And the tag we used to build the parser and the Lexer is YACC, Y-A-C-C. Nothing fancy. We are using the open source Go parser generator called Go YACC. And our grammar file, the YACC file, is listed here. Is all open sourced. Basically, if you want to write the MySQL-compatible SQL parser or wire protocol proxy, just don't repeat yourself. It is very boring, and you can just use TiDB's the SQL layer and the Lexer and Parser, and I think it is the most compatible MySQL parser in Go community. So I know some friends are building their own MySQL proxy using TiDB's parser. Yeah. And another reason we build a SQL layer from scratch is, just I mentioned, we want our SQL optimizer and the executor generates more precise physical the query plans. For example, if your optimizer knows the distribution information of your data, and it knows the underlying storage is a distributed system, and it should push down the computing logic down to the storage node and aggregate the partial data and send back to client, and it is more efficient. And notice that TiDB's SQL layer is stateless. Client can connect to any existing TiDB server instance. It is very serverless style. For example, the TiDB server just doesn't handle the storage. It just translates user's SQL statement into the underlying storage, TiKV, the key value operations. So you can send a request to any TiDB server instance. And well, just like I just mentioned, the underlying storage is TiKV, a key value, distributed key value store. Let's see how we map the relational data, like the rows, the table, to the key value engine. The architecture is very straightforward. The TiDB server translate the relational data to the key value API. And for example, we have a table called user. The ID is the primary key, the name, and the email. And this is the rules that how we map the table, the row data to the key value pairs. For every row, the data will be mapped to like using this rule. The prefix is table prefix, the row prefix, and this prefix is composed by the table name, table ID, and with the row ID. The row ID is your primary key. If you don't have a primary key, we will assign a invisible primary key for this row. And the index is just like the data row. It has the index prefix, and we put the data. We put the indexed data to the key value, the key part of this key value pair. And because the keys are ordered by the array in TiKV, so we can support the prefix scan. Yeah. Here's a little example of how we did this. For example, we have two rows. The primary key for the first row, the primary key is 1, and we put the primary key to the key part, and all the rest column data we will encode them into the byte array and put this byte array to the value part of the key value database. So basically, TiDB is a row-based database. It is not a column database like HBase, like Redshift, things like this. It is a row-based database, just like Oracle, MySQL, Postgres. So we don't support the very wide table, right? And also because the TiKV, the storage part, support ACID transaction in the key value at the key value layer. So all the index and the data inside TiDB are transactional and fully consistent. If you have the index, we will ensure that your data is there. It is all consistent. And yeah, this is an example of how we create the indexed key value pair like this. For example, let's say we have index in name column, and the index key is just like this. It is the index prefix, and the tom is the value of this row, and this part is primary key. So if you have a query like select stars from user where name equals to Tom, the TiDB server will compose to this key prefix, and it will get the primary ID of this row and compose another key value get to get this row. So if you are a point query, TiDB server will transform it to 2 key value get. Well, another big thing inside the SQL layer is optimizer. Actually, we build a cost-based model from day one inside the TiDB. And why we have to build a CBO is because the same logical plan will generate many equivalent physical plan, just like this. If you want to join 2 table, this is the logical plan. Just join and select a projection. It will generate, for example, 2 equivalent physical plan. We can use the hash join, or we can use the merge join. What should we use? So we need a model to find out which physical plan is the most efficient. This is the function or the cost model of TiDB, and as you can see, we introduced a network cost to our cost model. It is that is another reason why we decide to build the TiDB, the SQL layer, from scratch, because it's a distributed system. We have to transfer data from different nodes are very costly, so we have to introduce the network cost to our model. So on the other hand, TiDB will maintain the data distribution info and the histogram of the data distribution. The cost model will use this information. I will show a demo later, and you can see the query plan of TiDB. And with the help of our CBO model, we can support many join type. So I will put 3 most of our join type are these three. One is hash join, the sort merge join, and the index lookup join. The application developers don't have to care about which join operator the database will choose. It is chosen by the optimizer. And notice that just I mentioned, TiDB is a stateless architecture. It is because we are not going to reshuffle the data across different TiDB nodes. For example, if you want to join two very large table, maybe the TiDB will refuse you to do this without any index, without any hint, because we are not going to build a distributed hash table across different TiDB computing nodes. If you have such queries, you can use TiSpark. As Kevin mentioned, the Spark will help you to do this. It is how hash join works. I will explain a little bit. Hash join performs well processing the small and the medium-sized data. We have implemented the join operator and optimized it for the parallel data processing and make it streaming. So it is a streaming hash join. For example, to join two tables, TiDB will read the tables in parallel. Where for example, when reading the small table, TiDB will using the histogram info to detect which table is small table, which table is a large table, and it will put the small table in memory in this TiDB server's memory, and the data will be sent to several join worker inside the TiDB server. You can consider it as multiple threads. Inside TiDB is Go routine. Many Go routines. After the small hash table were finished, all the join workers will be notified and start joining in streaming and output the joined result. It is a typical hash join operator. SMJ, if you have two large table, but you want to join two large table, but the join them on the indexed column, the optimizer may choose the sort merge join. It will not cause a lot of memory to build a hash table. It just create the streaming connection to the different table and join them in the order. And index lookup join, it is a typical MySQL. I think MySQL only support this type of join. And this type of join is very straightforward, and it loads the data in batch and parsing the data and get the index of this batch and load this data from another table and join it. Well, let's talk about the transaction model. Because TiDB wants to provide a transparent transaction layer to the application layer. We don't have some limits like you have to join, you have to do transaction inside this server. We don't have these limitations. We can have transaction across different nodes. It is a distributed transaction. So the only way I think to implement distributed transaction is two-phase commit. So this is the only way we have. Our transaction algorithm is inspired by Google Percolator. It is a paper that describes the system Google built on top of build a transaction layer on top of big table, the key value database widely used inside Google. And the most important part of this system is it has a centralized timestamp oracle. It is like timestamp allocation service. Every transaction will talk to this component to get increasing timestamp for the conflict detection and resolve conflicts. So the problem is this the single point of failure? If your all the other part is distributed, highly scalable, but you still have a centralized timestamp allocator. Our solution is that our timestamp service is also a distributed system. It is one part of placement driver, just like Kevin said. The placement driver is our metadata storage service, but we will use Raft consensus algorithm to elect a leader to provide the timestamp. We embedded the etcd, the project etcd, inside the placement driver. Well, another must-have feature is online DDL, especially for the distributed relational database like this, because because it is a distributed database, some of our users may store, for example, one of our users store more than 10 billion rows in single table. That table across maybe 20 or 40 physical machines. If you just want to do some DDL, create some index, or add or remove some columns from this table, if your behavior like MySQL to lock the whole table, it is not doable. So we have to introduce a non-blocking schema change algorithm to this database. So our DDL algorithm is inspired by Google F1. It is a SQL implementation inside Google, and they published their DDL algorithm in this paper. Due to the time limit, I will not explain the algorithm in detail. We have wrote some blogs about this algorithm. It's not very hard to understand. We support online DDL, but the grammar, the syntax layer keeps compatible with MySQL. So you can use alter tables, things like this, just like you are using the standalone MySQL. But after you execute this query, you may find the DDL doesn't affect immediately. It is working the background. So yeah, there is some benchmark. We run some Sysbench. It is the standard benchmark for many relational database like MySQL, Postgres, Sysbench. Yeah, and all this benchmark you can find in our GitHub repo. This was to mention this diagram is compared to MySQL 5.7. The TiDB is a minimal deployment, three nodes, because we at least we have 3 replicas for every rows. And as you can see, the insert performance is insert throughput is higher because we use RocksDB underneath, and RocksDB is a LSM tree implementation, so it is more friendly to write workload. And why the select result is a little bit slower? Because we are, as I mentioned, it is a distributed system. We run the two-phase commit to guarantee the ACID semantic. So in this case, we have to need one more network round trip per transaction. So it is a little bit slower than MySQL, the single node. But we are still working on optimizing the select performance to be even faster than the MySQL. It is very promising, and so we will stay tuned. And as you can see, the important thing is that the throughput increase with more nodes. It is, well, the throughput increase with more nodes, the capacity, more capacity, and the latency is flat. The single that is what single node database cannot do. That is the beauty of the distributed system, right? And we build a bunch of tools that works with MySQL ecosystem to help MySQL user to use TiDB with little behavior change and good experience. That I will introduce some of them, and that is how we complement MySQL users. First tool is Syncer. Syncer is a tool to synchronize data from MySQL in real time. I will do a demo later. Let's take a look at this diagram. We have a MySQL master with binlog enabled, and the Syncer acts as a fake slave. When there is new data written into MySQL, the Syncer will obtain the binlog from the master and synchronize the data to disk and apply the rule filter. For example, we want to merge different MySQL shard to another one big table. Something that is or you can just skip some table. This is the rule filter, and send the raw data to either MySQL or another TiDB cluster. Some of our users try something interesting using Syncer. In the old days, for example, the different databases are separated. If you want to do some quick query like join or group by or some select join across different DB or across different MySQL instance in real time, it is nearly impossible, right? You cannot do join this table in this DB with another table in that DB. Sometimes we just can do this on the data warehouse like Hive, Hadoop, things like that. But some of our users, they use Syncer to synchronize all the different MySQL master into one big TiDB cluster as a huge MySQL slave. So you can run some join, because all the data are in one TiDB cluster, so you can run some join across different tables, across different applications using MySQL wire protocol and the MySQL syntax. That's how we call ourselves HTAP. You can use TiDB as a real-time data warehouse. And another tool is we call Lightning. It is a data import tool for TiDB. And how we import data before creating Lightning? Because we compatible with MySQL, so we can reuse the community tools like MySQL dump and MyDumper. Most of the MySQL users use MyDumper. It's an open source import export tool by corner. And we use MyDumper, and MyDumper will generate a lot of insert statements. And we use the loader, MyLoader, load this list, execute this insert statement to the TiDB cluster. But what is it is behind the insert statement? We do a lot of things like AST parse. The statement goes through the parser and goes through the query plan, the planner, the optimizer, and start the transaction and check the constraints, encode to the key value pairs, and write to the corresponding key value nodes. And this is a lot of work, and it is a little bit redundant. So we create this tool and skipped all this transaction part. We read the SQL statement and converted the insert statement directly into the key value pairs, and pre-generate the data file for the local RocksDB instance, and send the pre-generated data file to corresponding key value nodes, and the nodes accept this file and ingest it to the local RocksDB instance. And right now we support CSV format, and the data dumped by MyDumper. So here is a little use case. One of our users import, because TiDB Lightning is also a distributed system, so the performance can be scaled out if you have more physical nodes. This user only have 1, 2, 3, 4, 5, 6 TiKV nodes, and they import 700 gigabytes in less than 4 hours from MySQL to TiDB.
Excuse me.
Okay.
So that's TiDB nodes. How many compute nodes did it use?
The compute nodes. The storage node 1, 2, 3, 4, 5, 6. The computer node, you mean the Lightning or Lightning 3? In this case, it's 3. Just use 3.
And is it scalable if you
Add more Lightning nodes. Yeah, it is scalable, but at least 3. At least 3. Okay. Here's some user case. I will let Kevin talk about it.
So as Ed kind of try to set up our demo, I'm going to go through a quick use case overview. Who's using TiDB? So right now there are about 300 companies or so using TiDB in production in various kinds of workloads, like the 3 kind of use cases that I talked about earlier in the presentation. And one of the big users that I don't know how we're actually going to do this properly.
Okay.
In one laptop. No, it's okay. Sorry. Is Mobike, which is a very large Dockless bike-sharing company. Like I mentioned, they operate about 9 million of these smart bikes that you can just unlock or lock with your smartphone. You ride them to wherever you want. You lock them up. You go about do your thing. And with that, you do get a ton of data with this locking and unlocking sequence, essentially, right? That you need to make sure you scale them, you keep track of all of them, and it's very useful for the administrators of Mobike to actually find faulty bikes. If something's not working, if something isn't unlocking when it should be, they need to be able to, number 1, store all that data, which they use in TiDB, and number 2, be able to find those faulty dives really quickly, so be able to retrieve them, fix them, all that kind of good stuff. Another scenario is this kind of classic real-time analytics that they're using TiDB for. So they use a combination of TiDB itself plus Synchro, which Ed talked about previously. That's actually a proprietary tool that we are not open sourcing, but it's really good for large enterprises that are using MySQL and want to keep on using MySQL. And you essentially have this giant cluster of TiDB right underneath it, almost functioning as MySQL slaves in a way, from like an architectural perspective. And of course, they use PySpark as well to kind of cover the full range of analytical processing workloads. And the last use case they are using it for is this interesting loyalty program they call Mobike Store, where they kind of track all your activities. They give you points and rewards and all this kind of stuff, rewarding to use their platform to keep on using these bikes. And you can almost think of that as either like a bank or like an e-commerce situation where all this data needs to be permanently stored, so you can't lose somebody's points, right? Or they get really upset at you. And you run all kinds of promotional things to get them to use this more. So there's a lot of high concurrency traffic going on. And that is also what they use TiDB for. And this kind of stuff, you obviously can't suffer any kind of disruption, or there are plenty of other bike sharing companies that's going to take your business, right? And that's pretty much it. So I'm going to let Ed do a couple of demos. And in the meantime, let's do some Q&As.
For the Mobike, is that a single data center, or are they hosting it in multiple cities?
I think there are multiple data centers. I forgot how many.
They have a primary data center, and their application deploy in this data center. But some of their data replicate. The placement driver will guarantee there is a data replica in different data center, but all the leaders of this data will place into one primary data center. So even if the primary data center down, the election process will guarantee there is the new leader will have the newest data. There is no data loss, and the workload will redirect to the new data center. Like
It's a full copy in multiple regions.
No full copy. The copy is run goes through the Raft consensus algorithm. The Raft algorithm is the quorum-based algorithm. For example, if you have 3 data centers, the Raft will guarantee if you have a write operation, it will at least replicate to 2 data centers. So if your leader is down, the Raft algorithm will guarantee there is still 2 peer alive, and if they have an election, the peer who has the newest data will win. So it is like the quorum-based algorithm.
It works across the WAN.
Yeah.
Right. Yeah. Right. So kind of expanding. I think what you're trying to ask too is, does TiDB support geo-replication, right, across multiple data centers in different physical regions, not just across different machines? So yes.
Yeah, but the latency is have to guarantee by you.
The network. Bandwidth essentially. So the latency that has to do with that replication is kind of the quality of the network in the data centers, which isn't something that we can control when we work.
Physics. Physics. The speed of light. Yeah, and what's more, there is a bank in China have already used this architecture in their deployment. They have 5. They use TiDB to run their core banking system, right? The transaction, your bank account are already stored in this system. They have 5 data center. That means 5 replica for each row. But the write workload will synchronize write to at least 3 data center. So this architecture will guarantee if you have less than 3 data center crash or outage, the system still work. Okay.
Can you add and remove computing resources dynamically?
Yeah, because the architecture is dynamic Raft. It is run. The data region will split and merge dynamically, and the placement driver will move. Let's see the Let's see, the data inside TiKV are composed with many blocks, we set region, and the region is dynamically split and merged. For example, if you have a new cluster, it only have one block. When this
I'm gonna show them that we have a slide that just, I think there it is. Here we go.
Oh. And with the region become larger and larger, it will dynamically split into two smaller regions, like the cell splitting. And the placement driver will guarantee we will move the data from one node to another. And for example, the region inside the region, the data is quite nearly empty. The placement driver will tell them to merge into one cell again. So that is how TiDB dynamically scaling, right?
Right, and you can.
So by region, you mean a geographical region, or it's
Region is basically like a logical unit that we just call that, but you can call it like a chunk. Some people call
chunk, a split, range.
Right.
Yeah.
And just so for your information, a region in our world by default is 96 megabyte, but that's something you can configure depending on your use case. Like we typically don't recommend a region that's too big, but then you can start to form hotspots very easily. Then you have to do all these splitting, which we can totally do. But if you can avoid it, why not? And kind of going back to your point too. So yeah, you can definitely kind of remove nodes, right, or servers from the TiDB ecosystem or the whole platform as well. I guess typically we don't see people remove TiKV nodes as much because that's where data is actually stored and persisted. So if you're going to remove a node, you're probably actually deleting data or moving that data, somewhere else, which you can do, but we just don't see that happen a lot. But for like the TiDB MySQL layer that Ed was talking about, that's basically just like a stateless compute layer, right? So you can scale that up if you know there's a bunch of traffic coming in, and when that traffic is done for, you can scale that down, and that kind of helps you, kind of conserve your resources as well.
I guess the question really was, you say like you need to spike a job, where you're going to need, several billion records. You add a lot of resources like on Amazon or something, basically through a bunch of virtual machines.
Yeah.
And then you do it and you're done, you take off the data and you scale it out. I mean, you don't have to, what programmatically do you have to do to cut it down and make sure everything's done?
So from like our cloud, so we are building this thing called like a cloud manager essentially. You can think about it just like a control plane situation, and you can just like physically, well not physically, but like just click a few buttons and add more numbers of TiDB nodes, for example, right? And then it will take up however much time the network needs to spin those up, and then you basically have it. So the workload is pretty minimal. I don't think we can do that automatically yet because it really depends on what your workload is, right? Right. You probably don't want to just like do it because you want to have like cost transparency, right? For people who are using them too. You never want people just like, oh, we just spun up two because that's how you configured it 6 months ago, and then you're spending a bunch of money that you probably didn't need, right? So manually doing it is like super easy. Right?
And another, what's more, every region have multiple replica. The data, for example, in this diagram, for the convenience, I just use one replica of this region. Every region have at least 3 replica. It is according to your configuration. All these 3 replicas forms a raft group. It is a consensus group. So, for example, if you have one physical node crash or you delete one node, the placement driver will find, hey, there is some region miss one of its replica. So the placement driver, aka the brain, tells this region's leader, hey, you put another replica of this region in another nodes, things like this.
And who decides on the node that's available?
PD. The placement driver will keep a heartbeat to every physical nodes placement driver that the central cluster.
So there's a registry.
Yeah, it is registry.
That keeps track of the capacity.
Keep track the capacity and
CPU,
heap.
memory, disk.
Yeah, and the key value nodes will report its workload, region information, and is he alive, things like this, every 3 seconds to the placement driver leader.
Does the placement driver keep track of where the record is based on primary key or something, or it's always full search?
The placement driver will not care about the table schema, things like this. It just only keep the region.
It's like HDFS. It's like blocks.
It's like blocks. The placement driver just like the name node of the HDFS. It just keep the metadata of each region. And in this layer, the KV nodes doesn't care about the transaction, the table schema information. They don't care. They just see all these things are key value pairs. So the metadata of one region is just the start key and the end key. It's a range, right?
That means every query it would be full scan.
No. Fits within the range.
It fits in the range. For example,
Okay, I got it.
Yeah. Okay.
Good question over here.
Can you use TiKV directly?
Yeah, sure. The TiKV we just donate to the CNCF Foundation. We provide. You can use TiKV as a dropping replacement for HBase, but with a transaction API. You can use the transaction key value API, and you can just like, I don't know, check Foundation DB, things like that, but with a much better performance. Actually, we have some benchmark running the TiKV alone, but due to today is SQL meetups.
Yeah. We can share that with you guys.
Yeah.
And PySpark, is that just like a library?
Yeah, it is.
It's like a library or like a plugin of some sort, but it has like a wrapper around it where it has to communicate with the placement driver cluster, right? To retrieve the data location, and obviously it has to talk to the TiKV layer to get the data out of it. But that's pretty much all there is to it.
So you move the data into the Spark environment.
No.
Right. So
You move the Spark instructions to the data.
No. I'll move the Spark instruction to. Actually, I will expand it. TiSpark is a plugin for Spark SQL layer. We just hijacked the SQL SQL logical plan of Spark SQL and generate the physical plan and push down the computing logic, the Spark computing logic down to the TiKV storage node, and it will retrieve the data this query require, not load all this table data to the
results.
Yeah. So, and actually we expose the index information to Spark SQL Optimizer, so that in some cases we can use the index inside the TiDB and using the Spark SQL query, and also some of our users can write the query like this: one table in TiDB and another table in Hive or in other system. They can join. You can join it, inside the Spark.
Yeah, or you fire up the GCP now.
Sure.
Okay.
What makes TiDB faster than Foundation DB?
So there's a few kind of architectural differences. So I think Foundation DB, their storage engine, I think use SQL Lite or something. Yeah, so we use RocksDB, and so the storage engine that Foundation DB uses is a B-tree-based storage engine, and Rocks is an LSM tree based, and they have trade-offs essentially. So I think B-tree is really good for read, generally speaking. LSM has a better write performance because we wanted to build TiKV Overview to be this transactional database first, right? So we do want to optimize the write performance a lot more than Foundation DB did originally. I mean, I don't know what the guys are thinking now, right? Because it just got open source. Another difference is our replication model is different. So I think Foundation has this synchronous replication model. It's like a master-slave situation, and if anything becomes inconsistent, they have to like essentially restart the entire system. Though they promise to be under 10 milliseconds to be able to do it, so it's not like that disruptive, but that's kind of how that works. And because we use Raft, and it's like the election-based system, right? So as long as you have like an odd number of Raft replicas, default being 3, you can have 5 or whatever, and the election process works, then the entire thing is always available. So that is two of the kind of the differences there between us and our Foundation.
How is the number of replicas impacting performance? How is the number of replicas impacting performance?
So the more replica you have, definitely you will take a little bit of a performance hit. Number one, depending on how, with more replica, there'll just be more voting involved, right, in any particular RAF group. So, and depending on your network speed in between machines, not in between regions, but in between machines in one data center, that is kind of the cost that you factor into it. But based on our experience, the latency between machines within a data center is like super small, right?
Can you control where the replicas are placed? If you want to have them in different data centers, can you control this?
So they're all replicated kind of by default to give you high availability, right? But you can control where the leader replica lives, or not the leader kind of the element, right, within a RAP group lives, because that is the chunk of data you ultimately serve up traffic. So that has the most performance implication. So a lot of our users, say this bank actually that Ed was talking about, so they're a bank based in Beijing. They've got 2 data centers in Beijing. They have one somewhere else in China that's basically for just backup, right, disaster. So they would, or we would help them locate all the leader replicas to one of the 2 Beijing data centers, because that's where all their users physically are accessing their service.
Yes, but does this mean that the other 2 replicas will be in the other 2 data centers? Or is it always guaranteed, or it can happen that you can have all 3 replicas in one data center?
So there's, you can, but probably you shouldn't. Right, yeah.
No, I'm asking who decides this? How can you control and specify, you have 3 data centers,
right,
3 replicas. Can you control and make sure that they are all distributed, one replica in each data center?
Right, so that's controlled in the placement driver cluster.
Oh, so it's automatic, right? There is nothing you need to do.
Right, so it's automatically distributed, but then, depending, there could be situations where you do want to tweak them, and in the placement driver is where you tweak them, essentially, in a manual-ish sort of way. And there's a link out there that says TiDB Academy that I just want to tell you guys about real quick. It's this new program that we're rolling out in a month or 2. Basically, it's a set of courses that our staff is teaching online to tell people more about how to use TiDB, what are the differences between, say, TiDB and MySQL. I think our first course is actually geared towards MySQL DBAs who want to learn about the distributed system that works really well in the world. So that's something you guys can look up on our website, and you can sign up, now. So when we are ready, in about a month or so, we can let you guys know, and you can, hear more from us.
Now I want to share a demo using Kubernetes, using Google Cloud Platform. It is our project we called TiDB Operator. We put all these automatical deployment, scaling, operational knowledge into this project. And it's kind of like the plugin of Kubernetes. And it will launch a multi-tenant TiDB cluster in your Kubernetes environment. So you can hit this big blue button, and you will get the web cell here. And we put a step-by-step tutorial in this cloud cell. Actually, you can see it is in my GCP environment, and this command this command just set the project to my account and configure the computing zone. Continue. So let's launch a 3 nodes Kubernetes cluster. And all these steps are just setting up the Kubernetes cluster using GCP API. It is not deploying TiDB. So I will do it quick. Yeah, basically it is just pretty much the same you can create it in the dashboard, but I prefer using this cell. Blah, blah. At the meantime, TiDB also have a Docker Compose repo, so you can launch the TiDB multi-class TiDB on your laptop. The repo is PingCAP TiDB Docker Compose, and actually you can run the multiple Docker Compose setup in your laptop. Oh, I just stopped it. Let me just relaunch it. Okay. One command, you can launch a multiple nodes Docker Compose TiDB cluster in your laptop. Here, there is. I'm running 2 demos at the same time, so don't be confused. Okay, let's see the Kubernetes demo. Let's use Kubernetes control. You can see there's a 3 node. It is a 3 node Kubernetes cluster. And install Helm. Helm is you can consider Helm as a package management tool for Kubernetes. It is like apt-get for Ubuntu. So we put all our installation script to Helm, so the users can just use apt-get install TiDB and set up the cluster using Helm. All these commands just set up install the Helm. Okay, I think the Helm is successful. Well, finally we can deploy TeddyB Operator. And this command just install the TiDB Operator to your existing Kubernetes platform. We create some customer resource definitions for TiDB, and you can see the container is creating, and this is TiDB multi-tenant controller manager. Okay, it is running. We put all these operational things into this manager. Okay, and you can create your first TiDB cluster using one command. Helm install. We put a demo configuration, a demo charts of TiDB. Let's see the configuration file. Charts TiDB cluster values. For this deployment, the cluster name is demo, and the placement driver have 3 replicas. The version of the Docker image is 2.0.4, and you can change this number. For example, TiKV, the replica is 3, so we will launch 3 nodes TiKV. Okay, now all others. Voila. And we can see the Kubernetes will automatically creating the cluster we just saw. Okay, it is the first PD nodes. It is creating the container, and
So there's a sequence of creation.
yeah, the sequence
Driver first,
placement driver first,
and
then KV nodes second, and then finally the DB, the computing layer. Yeah. So that's why we put all this. We creating TeddyB Operator, because if you are not very familiar with this architecture, that will confuse you. So that's.
Does a KV need block storage?
No. In this case, we are using blob storage provided by Google, but in your on-premise deployment, you can use the local SSD file, local SSD disk, local disk. We don't rely on another distributed file system. Okay.
So with Amazon, you use S3 or EBS?
EFS.
Yeah.
EFS. We just consider the storage layer provide the POSIX API with
Use Parser.
POSIX API. So basically, you can mount S3 as a file system API, and you can run TiDB on top of it. But the performance will not be very good because it is a remote storage. Yeah. And it is my local TiDB setup, and we can launch a dashboard. It is dashboard for my local TiDB cluster. We just use the Grafana, just Grafana for this project. And let's say, okay, this cluster have successfully set up, and we can launch an we can expose the 4000 port and using a MySQL client to connect to the cluster. Hey, here we are, and you can see we just connect to TiDB cluster using a MySQL client. So we can select TiDB version. Okay, you can see this 204 and use test create table. Yeah. And same story in my local laptop. And actually, you can use the tools like MySQL Workbench to just connect to TiDB cluster. It is my local TiDB cluster. Okay. And you can use this Kubernetes cluster to create another TiDB cluster with all the we sharing the hardware because it is maintained by the Kubernetes cluster, and the Kubernetes will help us to do the isolation for different TiDB cluster. And another thing I want to demo is synchronize data from MariaDB or MySQL to TiDB. It is pretty simple. For example, we can I will put, okay, I have already have the MariaDB image in my local and this is the configuration needed by MySQL, because we have to change the binlog format to row. The syncer doesn't support mixed or binary format. It just supports row binlog format. Docker run. So we can run the local MariaDB in my laptop using this my.conf, and it will launch MariaDB for me. Okay, and we run a syncer. We run a syncer. I have already put the scripts, the configuration of syncer into the Docker image, so it is only one. Yeah, it just launched, and we can see the configuration file of syncer. And this command shows cat syncer tml. It is the configuration file of syncer. You can see you just specify from local MySQL port and host, and to 4000 port is my local Docker Compose TiDB cluster. And then you can open to MySQL, for example. This is MariaDB, and this is TiDB. Show databases. Okay, I create a new database here. Create database. Okay, let's see. TDT is here. Use TDT. Create table. TID name txt. Okay. Show table. Use. Okay, you can see the T is here. Insert into T values 1 hello. Okay, you can see the data is passing. This is my first time to demo. Okay, fine. It was, yeah, finally, yeah. For example, let's say TiDB will generate different query plan. Let's see. I have already loaded some TPCH data into my local TiDB cluster. So for example, we have TPCH. TPCH is a standard query benchmark for for OLAP database, it's more like the data warehouse query. It contains some very complex queries. I randomly pick up this query. It is select and with a sub select and join from and some group by, and it's not a select in the select. So let's see. TiDB will, this is the result. And as we can see, the query plan, we support explain statement. Okay, you can see this is the output. This is the query plan of this complex join. It is we display the query plan by the tree-based thing. So it is really straightforward for DBA to tuning the query. As you can see, this column we call the task. The task is the job type of this query operator. You can see there are two types. One is COP. COP means coprocessor, so that it means this operator is executing in the storage node, and the root task is the aggregation task. So this is the query plan. Okay, well, this is my demo today. Thank you.
So do raffle right now, and then we'll be around.
Who had? Oh, there it is. Oh,
I got a name in there.
Oh, you got to put a card in. Yeah, put a card in.
On my own card?
Yeah, your own.
I don't have this card.
Alright, we got to do the raffle next time.
We got two cards here together.
Hey, I put my name in. Does that count?
No, you got to put it right up. You have to have a real business card. You missed the announcement before.
Okay, put your name and email if you can.
Can you do it quick enough? Like 20 seconds, the whole room's waiting for you.
Well, get your pencil.
Anybody else want to get their card in last
My
chance?
name and what?
He said name and email.
Name and email works. I'll give you guys a piece of paper.
There, I got it.
You got it. Okay. Alrighty, let's see. Who's gonna raffle it off?
Two more over here.
Oh, there's a few more.
That is making their first business card.
You win for all of us.
Alright, so while they're getting their cards in there, we're preparing for the raffle. I just do want to let you all know that Kevin and Ed are here for one-on-one questions right after the raffle, and you are free to come up and talk to them, ask away. And who wants to actually win this?
Are you guys
No
here
way.
next week for Velocity?
We're not. Is that a? I don't have to. Oh, that's a.
The O'Reilly conference?
Oh no.
Just give me a quick meeting.
Anybody else?
Right?
I'm saying, alright.
Rather ridiculous.
Can I ask you to stick your head and just mix it all up?
There's a conflict of interest.
You're just mixing, you're not going to pull it. You can give it to someone else to pull it.
It's kind of like sand and ping pong balls. The ping pong balls keep rising.
Keep rising?
Yeah.
Can I ask you to look that way, put your hand in, pull out a card? Alright, read it out, read it out.
Okay, this goes to Ricky Nathan.
Don't blame us if your privacy is ruined.
Photo op.
While they're taking a picture, just don't come on up right now and start talking to them. Thank you all for coming.
Thank you.